Hello everyone, my name is Jingyun Yang. Here's my final assignment presentation. The first part is time series analysis. First, I do the data cleaning. First, I check whether there is any missing data. The results show that no missing values exist. Then I calculate the daily return of each asset. In the original data set, there are daily close price of each stock. Well, I need their daily return, so I use the following formula to calculate the daily return. Here is the key steps of KO assets modeling and forecasting. First, I do the stationary check. I visualize the original data, rolling mean and rolling standard deviation of KO. These three lines are all stable with some small fluctuations around zero. For further proof, I do the ADF test. These results indicate that KO's daily return is stationary. Second, I split the data into 8 to train and test sets. Third, I do the mean prediction. I use the auto-arrangement function, which loops through different combinations of PDQ and compares the AIC to select the best fitting model automatically. I fit the best fitting model ARIMA 002 on the train set and make predictions on the test set. The values are almost straight lines at zero. I calculate the RMSE and MAE between the prediction and test set. Their values are very small, indicating that the predictions are accurate. The mean value of the prediction data is 0.000368, which is KO daily returns mean prediction. Fourth, I use the rolling prediction method to optimize the ARIMA model. It uses all previous values as training set and makes predictions step by step. As the test set has 1007 data, I define the step length as 5 to shorten the calculate time. The result shows that optimization is not significant. This is probably because the original data is too stable to reflect the superiority of rolling prediction in overcoming the short-term memory of the ARIMA model. Fifth, I do the volatility prediction. I define a function called select Gauge model, which loops through different combinations of PQ in Gauge model and compares the AIC to select the best fitting model automatically. I define the range of P and Q as 1 to 5 to prevent the model from overfitting the train set. I fit the best fitting model Gauge 2-4 on the train set and make predictions on the test set. The values are almost stable near 0.01. I calculate the RMSE and MAE between the prediction and the test set. Their values are very small, indicating that the predictions are accurate. The mean value of the predicted data is 0.010445, which is KO daily returns volatility prediction. Sixth, I use the rolling prediction method to optimize the Gauge model. Similar to the rolling prediction I described before, as the test set is too big, I set the rolling step length to 5. The plot shows that the optimization prediction is much closer to the true value than the original Gauge. This means the optimization improves the accuracy of the prediction. After doing above steps to the other 4 assets, I finally get a prediction of all the 5 assets' daily return and volatility. Then I arrange them in the table. We can see that in our prediction, GPM has the highest daily return and volatility, so it may be the high-risk, high-return stock. KO has a low daily return and the lowest volatility, so it may be a low-risk, low-return stock. The second part is mean variance optimization for portfolio construction. First, I calculate the mean return and risk of each asset. The result is pretty close to the prediction in 1.3 part. GPM is high-risk, high-return. KO is a low-risk, low-return. Second, I calculate the covariance matrix of the assets. The values on the diagonal line are variance of assets themselves. GPM is the most risky, while PG is the least risky. The values on the off-diagonal line are covariance between different assets, closer to 1 indicating that they move in the same direction, closer to -1 indicating that they move in the opposite directions, closer to 0 indicating that there is no significant linear relationship between them. The values here in the table are close to 0, so there is no significant linear relationship between the 5 assets. Third, I use Monte Carlo simulation to generate the efficient frontier of 5 assets. I set the random seed to 42, define the number of randomly generated portfolio as 20,000. I then loop to generate the random weights for each portfolio and calculate the annualized return, annualized volatility, Sharpe ratio, and utility function. Sharpe ratio measures a portfolio's exit return per unit of risk. The utility function helps investors select the optimal portfolio by balancing expected returns and risk. The following are the equations of the above 4 things. After doing the Monte Carlo simulation, I plot out all the randomly generated portfolios' risk and returns. The highlighted dot is the max Sharpe ratio portfolio. The blue line is the efficient frontier. These portfolios on the efficient frontier has the highest expected return for a given risk or the lowest risk for a given expected return. Alice prefers the tangency portfolio, so she should choose the portfolio with the maximum Sharpe ratio. Bob prefers the portfolio for max utility. Their choices detail are as follows. The first 2 rows are Alice and the second 2 rows are Bob's. The third part is principal component analysis for return allocation. The color intensity for each square in the heat map indicates the correlation degree between the 2 variables. Lighter colors denote stronger correlation, darker colors imply weaker correlations. In my observation, WBA appears the darkest. The other stocks have lighter colors. WBA operates in the drug retailing industry, which is closely related to people's health. The other stocks belong to industries such as technology, financials, which are closely tied to global economy conditions. So the correlation between drug retailing and other industry are lower, while the correlations among other industry are higher. What is PCA? PCA is a method to reduce the dimensionality of features in a dataset and retain the most important information. Why is PCA used in data analysis? Analyzing a dataset with all the features may lead to overfitting problems. PCA reduces the dimensionality by transforming the original features into a new set of fewer features, which are linear combinations of the original ones. This improves the generalization of the model and reduces the computing cost. Here is the key steps of PCA. First, standardize the datasets feature to a standard normal distribution with mean equal to 0 and variance equal to 1. Otherwise, features with large values will dominate the result. Second, feed the PCA model on the train set and get the principal components. I plot the first 10 principal components, explain variance ratio, and cumulative explain variance. We can find that the most significant factors explain approximately 40% of the daily return variation. The top 10 factors together explain approximately 70% of the daily return variation. The contribution of the rest of the factors are relatively small, with only a sum of 30%. I plot the Sharpe ratio of all the portfolios generated by the PCA modeling. Portfolio 18 has the largest Sharpe ratio, equal to 0.338, which might be the best portfolio I want to find. Portfolio 18 has the highest Sharpe ratio. However, in the left plot, its return dropped sharply in September 2019 and has been stabilized at around 0 since then. This indicates a poor performance. In the right plot, there is some concentration on the stock weights. Some stocks have relatively high weights, which makes the portfolio very sensitive to price changes in these stocks. Combined with the events that took place around September 2019, the US and China announced that they would improve the tariffs on each other's goods, which negatively impact the export business of companies in the technology and manufacturing industry. International crude oil prices have fallen. Energy companies' stock may have poor performance. COVID-19 outbreak in September 2019. The supply chains are blocked, leading to an increase in production costs. The global economy was subdued, leading to a drop in market demand. As a result of the above events, some of the heavily weighted stock in Portfolio 18 have performed badly since September 2019, which impacts the performance of the overall portfolio. Portfolio 8's Sharpe ratio is not the highest. However, in the left plot, its return continues to rise from September 2019 to December 2022. After that, it starts to fall, but it's always higher than that of the eco-weight portfolio. This indicates a really good performance. In the right plot, portfolio's heavy weighted stocks are mainly related to healthcare, technology, and the communication service sectors. COVID-19 outbreak in September 2019. So the healthcare sector has a good performance due to the increased demand for medical equipment and medicines. The technology sectors, such as Apple company, has a good performance due to the increased demand of its popular products, such as iPhones, iPads, Macs, driven by the trend of remote working and online learning. The telecommunication service sector has a good performance due to people's more frequent use of phone calls, the internet, etc., to stay in touch and work online. As a result of the above events, some of the heavily weighted stocks in Portfolio 8 have performed better since September 2019, which impacted the performance of the overall portfolio. As COVID-19 ends in 2023, other stocks begin to recover, so Portfolio 8 declines slightly. However, as healthcare remains highly valued after COVID-19 and online working has become popular, the portfolio continues to perform well in a recovering market environment. Portfolio 0 in the left plot, its performance is similar to the eco-weight portfolio. There is a slight rise from 1 to 1.8 during the test set period. In the right plot, the portfolio's weight is also close to eco-weight. This is because when using PCA for portfolio optimization, the first eigenvector is usually assumed to represent the market risk. This means that the portfolio is more influenced by the market as a whole rather than by individual stocks in the market, so it's similar to the eco-weighted portfolio. The fourth part is hierarchical risk parity. First, tree clustering, calculate the distance between all clusters, then merge the two closest clusters and iterate above two steps. HRP is a method to diagonalize the covariance matrix by reordering a set. Recursive precision aim to reduce risk by assigning more weights to the less variance sets. The following are the key steps of it. By looking at the tree cluster results in the plot, the different colors represent different clusters. There are 3 clusters in the dataset. Most stocks in the first cluster are in the healthcare industry. Most stocks in the second clusters are in the technology industry. And the third cluster contains multiple industries, but they face similar market risk factors. I visualize the portfolio weights for all types of asset allocation after recursive dissections. WMT, GNG, MCD, and PJ have the highest weights because during COVID-19, customers focus more on basic lifestyle needs and healthcare, which are this company's industry. And this company's leadership in their industry allow this company to better respond to changes in the market and maintain stable profitability. According to the plot, the cumulative return curve of the HRP portfolio does not rise or fall dramatically and shows a smooth and slight increase, which indicates that this portfolio has a good risk tolerance. The standard deviation of the HRP portfolio on the out-of-sample data is 0.197, which is lower than all the above portfolio generated by PCA. This indicates that the HRP portfolio has the least risk. The Sharpe ratio of the HRP portfolio on the out-of-sample data is 0.497, which is higher than all the above portfolio generated by PCA. This indicates that the HRP portfolio has the highest return per unit of risk. In conclusion, the overall performance of HRP portfolio is better than PCA portfolios.